Physics classroom today, looking at some AP Physics C electricity and magnetism questions. Specifically, we're going to be looking at the year 1999, question 3 of the AP Physics C E&M exam. It has a ring of charge, and we're looking at some distance away from that ring, what some different potentials and electric fields are. So let's take a look at this problem here and see what we got going on. They figured out how to ever get rid of the bells. I'll be so happy. The non-conducting ring of radius r shown above lies in the YZ plane, so it's lying in a plane, and it carries a uniformly distributed positive charge. So it's nice that this is uniform here. It's very important for us. If it wasn't, we'd have a bit of a headache. And the charge is Q. We're looking for the electric potential, also known as a voltage, at points along the x-axis as a function of x. And that's really important there, because as we're looking along this x-axis here, as that goes out, we want this potential function to be as a function of that x position. So what we can recognize is that the voltage has an equation of kq over r, but that's for a point charge. On our case here, we actually have small elements of charge dq that go all the way around the ring. Now what's really nice here is when these charges are some distance away from some point, we'll just label it x, these charges are all the same distance away, no matter where they are on the ring, if they're on the top or the bottom, or if they're on the left or the right. You know, if you just thought about twisting the ring like this, they're all the same distance away. And because it's a uniformly distributed charge, all of those small charge elements are providing the same amount. And since that the potential, or the voltage, is a scalar quantity, if we added all of these tiny little charge components together, they would just give us the total charge. So we can actually say here, due to the fact that the distances are the same and the charge components are the same, we can just say that our voltage is equal to kq, the total charge of the system, divided by r. But that doesn't give us as a function of x. This is a function of r. Well, if we draw this ring edge on, that's our x-axis. That's the top of the ring. That's the point. This is r. But what we want is we want to know, what is this as a function of x? Well, the other quantity we do happen to know here is that the ring has some radius, capital R. So if we just put this radial distance in terms of x's and r's, that'll give us what we want. And with a simple Pythagorean theorem, we can say that that distance r is just equal to r squared plus x squared, which means that down here we can say that this is equal to kq over, and I'm going to write this with parentheses. You could write it with a radical sign if you want, but I like it like this. There's our bell. So that's our first answer for the potential along the x-axis. Now in part B, we're trying to show that the x component along the electric field of the axis is given by this big equation, and what are the y and z components of the electric field along the x-axis. It's actually easier to do part 2 here, looking at the y and z components of the E field along the x-axis, because what we actually see is that the components running in the z-axis or the y-axis here, they're actually always going to cancel out. There's an equal amount pushing left and right and up and down from every single orientation or angle possible in this case. So we're actually going to see that in both the y and z direction, we're going to get 0. And it's simply due to symmetry. Even if the answer is just 0, I still like to say that it's due to symmetry to let a grader know that, hey, I understand what's going on here. These are vectors. Due to the symmetric nature of it, they're canceling out. So I would just put 0 due to symmetry there. Now, A is the slightly harder part of this problem. If we're looking for an electric field, we could solve this by looking at tiny elements of the ring and then adding up different components of them and working forward. for an electric field, but a slightly easier way to do it is to recognize that the electric field can be given to us by the negative of the derivative of the voltage as a function of position. And in our case, the position we have isn't of r. Our position is actually of x here. So what we're going to do is we're going to take the opposite derivative of this quantity, and that quantity is going to be kq over the quantity r squared plus x squared to the 1/2 with respect to dx. And now we just need to do a little derivative here of this. And if we can take that derivative, we'll be good. An important thing for us to recognize is that the only thing we are taking with the derivative with respect to is x here, and we only have this x. Everything else is a constant. So constant, constant, and a constant that we need to just kind of ignore for a little bit. If we rewrite this, it might be easier to say the negative derivative of kq times the quantity r squared plus x squared to the 1/2 to the negative 1/2. I just brought that quantity in the denominator up into the numerator, made that exponent negative. So now, when I go to take this derivative, I can see that I get, well, taking my power and pulling it down in front, I'm going to get negative times negative 1/2. There's my kq. Here is my quantity, r squared plus x squared, minus 1 from that exponent, so negative 1/2 minus 1 is negative 3/2, and then multiply that by, using the chain rule, the derivative of what was actually in our quantity as well. R is a constant here, so the derivative of any constant is just 0, but the x squared is going to become 2x for us. If we play a little bit of cleanup, we see that our answer here is kqx over r squared plus x squared to the 3/2, moving the negative exponent into the denominator. If we take a look at this answer and compare it to what we had, well, here we've got qk over r squared plus x squared to the 3/2. The 1 over 4 pi epsilon naught is the value k. So we're good there. We took a great derivative. Not that bad. For part C, we need to determine on that electric field which we just created, which is that equation, where is there a value on it that the E field is at a maximum. And what we have to do here is a little bit more calculus. If we think about any generic function, if you wanted to find where we had a maximum or a minimum, you would need to find where the slopes are equal to 0. Well, a slope is just a derivative, so if the slope or the derivative equals 0, then what we're really saying here is that the derivative of the electric field as the x position needs to be set to 0, which means that what we can say here is that the derivative of and then kqx over the quantity r squared plus x squared to the negative 3/2 with respect to x has to equal 0. Now there's two ways you can solve the derivative of this term right here. The first way you can do it is just by recognizing that you have an x in the numerator and an x in the denominator, and that means you have to use a quotient rule. You could say that this top term is f and the bottom term is g, and that will allow us to say, using f prime, or the derivative of fg minus the derivative of gf all over g squared. Or what you could do is you could take that negative x, or that you could take that exponent in the denominator, which, oh, I made a mistake. I wrote that as a negative, didn't I? That's not a negative. It's a positive. You can take that denominator and move it into the numerator by making the exponent into a negative, and then you can use the product rule there. Some people feel more comfortable than that. We're just going to use the quotient rule here because why not? You know, quotient rule is a good thing to practice. So if I take a look at this top function, I'm going to take this kq just outside. It's just a constant. So here's the kq. The derivative of the top function is just the derivative of x, which is just 1, and then times the bottom function, which is r squared plus x squared to the 3/2, minus, well, the derivative of the bottom function is, this is a power chain rule, so there's your 3/2 times r squared plus x squared to the 1/2 times 2x, and then times the numerator function, which is just x, and then all over the denominator, which is r squared plus x squared to the 3/2 squared. So I'm just going to call this the 6/2. That looks like a lot, but it actually cleans up nicely. When we look at just the first term here, leaving that kq on the outside, we see that the 3/2 in the numerator and the 6/2 in the denominator give us just 1 over the quantity r squared plus x squared to the 3/2 as they cancel or divide out. And then we end up getting on the right side that our 2's divide out, so we get minus 3 times the quantity r squared plus x squared to the 1/2 times x squared all over. And then because I still have this r squared plus x squared to the 6/2 in the denominator, what we're going to find is it's actually going to eliminate this in the numerator here. And in my denominator, I'm just going to get r squared plus x squared to the 5/2. So I'll just tighten this up a little bit. And this equals 0, because that is the derivative, and we've set it equal to 0 to give us a maximum or a minimum. So looking at this here, how can I solve for a value of x? Because this looks to be a pain. Well, a quick little trick of math is that if you've taken out constants from this larger term here, this k and q, if I divide them from each side, I can just actually get rid of them, because 0 divided by kq is still going to be 0. So I'm left now just with the 1 over quantity r squared plus x squared to the 3/2 minus 3 x squared over r squared plus x squared to the 5/2 equaling 0. I'm going to take an entire side of it and move it over. Just add that over, so I get 1 over the quantity to the 3/2, that's the r squared plus x squared, equaling 3x squared all over r squared plus x squared to the 5/2. If I multiply each side by r squared plus x squared to the 5/2, what will happen is this side will cancel out, and on this side I will now have a r squared plus x squared to the 5/2, which allows this entire denominator to go away and that to become a 2 as those divide out, which leaves me with just the quantity r squared plus x squared equals 3x squared. I'll subtract an x squared from each side, which gives me that r squared equals 2x squared. And then if I go ahead and solve this for x, I find that r squared over 2 equals x squared, and that means that finally, after all that work, x equals r over the square root of 2. And technically this answer here is plus or minus, but we're only going to use the positive because you can only be a positive distance away from things. So that is the maximum position at which you are going to have a maximum E field. So that is the position at which you will have a maximum E field for a ring of charge, okay? Now, if I actually saw this type of question on the AP test where I was like, I got to do a quotient rule, and then I got to like solve all this out and do this work, I would have personally stopped doing work all the way up here unless I had some time. Because getting to that point where it's like I have to do the derivative and this is the thing I'm taking the derivative of and setting it 0, you probably got a point for saying that when the slope is 0, and you probably got a point here, and you got a point here. So if that's 5 points sitting there, you just picked up 3 of them. I'm not doing all of this work to get one last point for the actual value. Like, that's just a lot of work there for maybe a point or two. So unless you've got some free time on your hands or you feel really, really good about your derivative skills, or if you're doing integral calculus or integration, I normally just leave it. Leave it till later. The math is still going to be there. Just wait on it. It's also something where, you know, if you set up this derivative incorrectly to begin with, you might not get the right answer anyways. So all of this work here could possibly still be wrong because you just set it up wrong to begin with, or you had some bad value all the way back in the beginning. So because you're not exactly sure, if you're, you know, a little hesitant, just don't worry about it. Just leave it. Just say, hey, you know, my answer that I get for the maximum, I'm just going to make one up. The answer is, you know, I'm just going to call it like some other letter. I'll call it tau. Okay, and just circle it and walk away. Because we still might need that answer or a answer, but it's just not worth trying to do all of that math unless you feel really, really good about it. Okay. Once you do have your value, though, even if you do just set E equal to tau, to find the maximum electric field, then we just need to go put that value of x into that initial equation we had all the way up here. So we're just putting in a value for x. So in this case, I can just say that, and we still don't have numbers for r, so this is all going to be numeric. We can say E max is just equal to kq, and then this would be whatever your answer is. If it's tau, if that's what you like guessed an answer, like I didn't know, but I've just got to put something, then put a tau in there. If you said it was 17, put a 17 in there. For us, the true answer is actually r over root 2. Okay? And then divided by the quantity r squared plus r over root 2 squared to the 3/2. That's your answer. So if you don't know what it is, just say that and that or the previous answers from before and you didn't know what it was, you're still going to get points for that because you're consistent within your work. On the axis below here, we're asked to sketch the E field versus x for points on the x-axis from negative 2r to positive 2r. Well, now we might need to start having a proper answer to properly sketch this graph. If we don't have that, it makes it a little bit harder. In the end, the graph will look something similar to this and then turn the other way. It should be pretty symmetric, you know, just a quick little sketch there. And if we place an electron at x equals r over 2 and release it from rest, what's going to happen to it? Well, let's go back up and look at the ring itself. If we put an electron on the x-axis, and this entire ring here was positively charged, then what's going to happen to this electron is it is initially going to be attracted, and it's going to move along this x-axis back to the center. And as it's being attracted, it's going to speed up until it reaches that exact center position. That center position, it's going to be at its maximum speed, and when it goes through to the other side here, it's going to be pulled back. It's being pulled back, but it's still moving forward with some velocity. So it's going to be slowing down. It's going to reach some position out here, symmetric to wherever it started. It's going to stop, and then it's going to fall back towards the center of the ring. It's going to pass through the center, and it's going to go out, stop, and then turn back again. So we're actually going to see for this last little bit, if we are going back and forth, and if there's no friction forever, then what we're actually going to see is we're going to have simple harmonic motion. The electron will oscillate through the ring. And this last part there, we're just saying it's simple harmonic motion that the electron will oscillate. That was 2 points right there. Just for saying simple harmonic motion, the electron will oscillate through the ring. That's 2 points. All of this math was also 2 points. Get the easiest points you can. You know, like I said, there's definitely things in a problem that are a little easier than others. Make sure you do the stuff that you're able to do, because, you know, if you've only got 15 minutes to solve a problem out, the bulk of this time we spent here was just doing the calc, and you don't always need to do that, okay? You're just trying to get as many quick points as possible in the time we have. So that was the 1999 AP Physics C E&M question number 3, excuse me, with a ring and looking at its E field and voltages. But with that, this problem's finished. Take it easy.